Hello, good evening. Right afternoon, no one joined.
Whereas I was since there was
O-
no message.
Okay, no problem. Okay, let's wait for a moment and then we will start. Even now, only you have joined. Just let me put the method. Lokesh, Charan. Okay, let's start now. Right, so we were discussing about what? The magnetic field, right? And in the magnetic field, first we discussed about the permanent magnet. Okay, permanent magnet, what will be the strength of a a bar magnet that is given by the magnetic dipole moment, right? So more the magnetic dipole moment uh, a magnet has, the more will be the magnetic strength of a bar magnet. Okay, and what is the direction of magnetic moment? So direction of magnetic moment or magnetic dipole moment is from south to north pole. Okay, and we cannot have the isolated north or south pole. Means however small a magnet is, we are always going to have what? The north and south pole of a magnet. Even you break it into micro level, the uh, magnet will still have the north and south pole to it. Okay, so if we talk about what will be the magnetic field line for a bar magnet, let's try to learn for that one first. Okay, so magnetic field lines, it always form what? It always form the closed loop. It always form the closed loop means what? That if a bar magnet is there and if we try to draw the magnetic field lines of a bar magnet, okay, this is the south pole and this is the north pole. So outside the magnetic field is what? Coming out of the north pole and entering the south pole. This is outside the magnet. And what about inside the magnet? Inside the magnet will be from south to north pole. Okay, so that's why magnetic field lines of a bar magnet, it always form what? It always forms the closed loop. Understood? So that's why if you write what is the magnetic flux through a closed surface, okay, please keep in mind we are talking here magnetic flux through a closed surface. So if you write the magnetic flux through a closed surface, it is always going to be what? It is zero, right? Why? Because for a closed surface, when we are saying, okay, please keep in mind it's a closed surface. So for a closed surface, what will happen? If we write B dot dA, okay, B dot dA is what? It is the magnetic flux. Okay, B dot dA is what? It is the magnetic flux. So for a closed surface, B dot dA is always going to be what? Zero. And that is called as what? The Gauss law for magnetism. Right? Gauss law for electrostatic we have written. This is what? The Gauss law for or Gauss law of magnetism. Clear? So, as per the Gauss law of magnetism, what will happen if we have a closed surface, right? Then the net magnetic flux through a closed surface is always going to be what? Always going to be zero. Understood? So, this is the magnetic field lines outside the magnet. What it will be from the north pole towards the south pole, right? Or you can also say that outside the magnet the field line is coming out of the north pole and entering the south pole, and inside the magnet it is from south to north pole. So that's why one point you can note it down, that magnetic field lines, okay, magnetic field lines are always magnetic field lines are always forming the closed loop, always forming the closed loop, not like the electrostatic field line. Electrostatic field lines are what? Never forms the closed loop, but magnetic field lines, due to any bar magnet, if we are going to draw it, it will always form the closed loop. Okay, so understand about this magnetic field line thing? Please tell me. Now, the next thing is what? If we try to calculate what will be the magnetic field, what are the factors on which the magnetic field is going to depend? Okay, so magnetic field depend on, if I am calculating the magnetic field due to a bar magnet. Okay, so let's first write it. What is the magnetic field? Magnetic field due to a bar magnet. Okay, so as we go away from the bar magnet, what is going to happen? The magnetic field lines are going to, or magnetic field, what we can say, it is going to decrease. Okay, and here we are writing the formula for what? Keep in mind, for short bar magnet. What kind of bar magnet? For short bar magnet we are going to write it. Okay, so there are two important points where we have to write the magnetic field. One is called the axial point, other one is called as the equatorial point, right? And we are going to measure the distance of the point from where? From the center. Okay, so from the center of the bar magnet, let's say the point is what? R distance from the magnet. Okay, so here we are measuring the distance from where? We are measuring the distance from the center of the magnet. Okay, at a distance R we want to calculate. Can you tell me what is this point? Can I call this point is the axial point? Please tell me. This is the axial point. The magnetic field on the axis of a bar magnet is what? It is mu naught by 4 pi 2m by r cube. Mu naught by 4 pi 2m by r cube. That means here, if you see the magnetic field, if you are calculating due to the bar magnet, okay na, on the axial point, how much it will come? It will come mu naught by 4 pi 2m by RQ will come. And if you write the direction, the direction of magnetic field on the axial point, that is in the direction of the bar magnet as well. Direction of what? The bar magnet or magnetic moment, you can say that, because this is the direction of the magnetic dipole. So if you write in the vector form, you can also put it here, the vector and vector sign. What is the mu naught called? Can you tell me what is the mu naught? Mu naught is called the permeability. What is the mu naught? Mu naught is permeability of medium. If the medium is vacuum, we will call it permeability of vacuum or permeability of free space also, you can say that, okay? Permeability of vacuum or permeability of the free space, you can say. So if you change the medium, what will happen? The permeability of the medium will change. Permeability means what? How much quickly or how effectively a medium is going to get polarized. That is the meaning of the permeability of a medium. Okay. So mu naught is for what? For the vacuum. Okay. And for different medium, what will come? For different medium, the value will come different. Understood? Now, another point we have where we want to calculate the magnetic field line is, let's say, this point. What is this point? This is called as the equatorial point. Equatorial point means what? The point which is at the perpendicular bisector, which is where? At the perpendicular bisector. Again, we are going to calculate at a distance r. The magnetic field on the equatorial point. How much it will come? It will come mu naught by 4 pi m by rq. Mu naught by 4 pi m by rq. And if you calculate the direction will come opposite of the dipole. Okay. So this is the magnetic field on the equatorial point. Okay. So if I want to write it in the vector form, can I put the vector like this? This is the vector. And here, should I put a minus sign here? Because on the equatorial point, the direction of magnetic field is what? It is opposite of what? Opposite of the dipole direction. Clear? So on the equatorial point, the magnetic field will be what? It will be opposite of the dipole direction. Clear? So this is the magnetic field on the axial point and equatorial point. Clear? Let's take an example and try to understand how do we calculate the magnetic field at a different point. Okay. Let's say in the question what is given to us, this is the coordinate axis. Okay. X axis and y axis given to us. Okay. This is the x axis given to us. This is the y axis given to us. Okay. And we are going to put a dipole like this. One dipole, I kept it like this. What is this arrow represent? This arrow represent the direction of what? Direction of the dipole. This dipole magnetic moment is M, and there is one more dipole that is kept along the y-axis. Okay, blue dipole. Let's say its a dipole moment is also what? The same. And one more thing is given in the question, that these two dipoles are what? The short dipole. Okay, these two dipoles are what kind of? These two dipoles are the short dipole. Now they are asking, there is a point on the x-axis somewhere here. Okay, in the question they gave, there is a point on the x-axis here, and that distance is given as something r. So now the question they are asking, find net magnetic field. Okay, find net magnetic field at the given point. Okay, so here net magnetic field at the given point, if I'm calculating, who will create the magnetic field there? Can you tell me? Can I say that both the dipole are going to create the magnetic field at that point? Isn't it? So let's calculate both of them, and after that how we will add them? We will add them vectorially. Understood? So please tell me how much is that coming? Please try it and tell me what is the net magnetic field at this point is coming to us. The medium is vacuum only, okay na? The medium is what? Medium is vacuum only, okay? So please calculate the net magnetic field at that point and tell me how much is that coming. Calculating that? Just calculate for both the dipole, okay na? So for that black dipole, what kind of point is that green point? The point is the axial point. And for the blue dipole, what kind of point is that? It is equatorial point, right? So apply the formula of axial magnetic field and equatorial magnetic field, okay? How much coming? Tell me. See, due to the black dipole, if you are calculating, what is the magnetic field come? Axial point. On the axial point, the magnetic field is what? It is in the direction of dipole. Let me call this magnetic field as B1. How much B1 will come? Mu naught by 4 pi 2m by r cube. Okay. For the blue dipole, the point is equatorial. And equatorial point, the magnetic field is what? In the opposite direction of the dipole. So that's why the direction I have drawn, it is in the opposite of the dipole direction. Okay. So B2, how much it will come? Mu naught by 4 pi m by r cube. So if you want to write the net magnetic field, what you will write it? You will write it mu naught by 4 pi 2m by r cube, that is in the I cap, right? And what next? The next one is mu naught by 4 pi m by r cube, that is in the minus j cap. So if the question asks it in the I cap j cap form, this is what you will write your answer. If the question only asks what is the magnitude of magnetic field, so what we will do it? We will find out the magnitude of that one. Mu naught 4 pi m r cube, all are common, right? Under root of what? Under root of 2 square plus 1 square, right? So root 5 will come. Understood? So this is the net magnetic field at this point. So we should apply what? Axial and equatorial formula depending on what? Okay, depending on what kind of point is that one. So please tell me clear about how to calculate the magnetic field on the axial point and equatorial point. And keep in mind, we are writing it for the short dipole. Okay, we are writing it for what? For the short dipole, we are writing the formula. Okay, let's take another example. Okay, in this example, what is given to us? You can learn this as a formula, or you can learn this as a result, as a question also. The question gave what? There is a dipole given to us. Okay, there is a dipole given in the question, something like, let's take it here. This is the dipole given to us. Okay, it's a short dipole of dipole moment m, and the point is given what? Somewhere here. The point is making what angle? Theta angle with the dipole direction. And what is the distance of the point? The distance of the point from the center of the dipole is r. Now, in the question, they are asking that what will be the uh, magnetic field, net magnetic field at this point. So here, can you tell me what you are going to do it to calculate the net magnetic field at that point? If I ask you in this question, what is the net magnetic field at this point? What are you going to do it? Please tell me. We also said, how do we calculate this magnetic field, right? So do one thing. Last question, when you solved it, what happened? The dipoles were already given in what? In the two perpendicular direction, and from those two dipoles you had to calculate the magnetic field at this point. In this question, what happened? The dipoles are not given in the two perpendicular direction. So to calculate the magnetic field at that point, can you take the two component of the dipole? So that for one component, the point becomes axial, and for the other component, the point becomes equatorial. Understand? Please tell me. For one component, like if I take the component of dipole, can you tell me what is this component will come? This one will come m cos theta. And what about the other component? Other component will come m sin theta. Dipole is a vector quantity, and you can always take the component of a vector. So please tell me, for m cos theta, what kind of point is that? For m cos theta, what kind of point is that? Is it the axial point? For m cos theta, what kind of point is that? Is it the axial point? And for m sin theta, what kind of point is that? It is equatorial point. So please tell me, what are the values coming? Can you calculate now? Please tell me, can you calculate now? For m cos theta, what kind of point it is? It is the axial point. Okay. And for m sin theta, what kind of point is that? It is the equatorial point. Okay. So let's calculate the magnetic field due to these two components. Okay. Please calculate it and tell me how much is that coming. Calculating. Calculating due to these components. Please tell me. Calculating these two due to these two components.
What's it?
Hmm? Are you calculating due to these two components?
Yes,
What are
sir.
the values coming? Yeah, please calculate it and tell me how much is that coming. Due to m cos theta, what is the magnetic field will come? So for m cos theta, the point is axial. So value will come how much? So for m cos theta, the value will come mu naught by 4 pi 2 times of m cos theta by r cube. And for m sin theta, the point is equatorial. So field will come like this. Value will come mu naught by 4 pi m sin theta by r cube will come. Now to get the net magnetic field, what you should do? You should find out the resultant of that one. It's not a vertical line. Please keep in mind, this is not the vertical line. This is making some angle alpha here. So if I ask you, what is the net magnetic field magnitude? So what you will write it? Under root of mu naught by 4 pi under root of, just see those two values. Okay, now just see these two values are known to us. Both are perpendicular component. We can find out the resultant of those two, isn't it? So how much is the value coming to us? Mu naught by 4 pi 2m cos theta by r cube square plus mu naught by 4 pi m sin theta by r cube square, isn't it? Now just simplify it. Mu naught by 4 pi common, m is common, r cube is common, under root of 2 cos theta square, that means it is 4 cos square theta, plus Sine theta square, that means another sine square theta, isn't it? One of the cos square theta, you can bring it outside. It will become mu naught by 4 pi m by r cube, right? And it is coming 1 plus 3 cos square theta coming to us. This is the net magnetic field at that point. This is also called as magnetic field due to a dipole at a general point, not the axial, not the equatorial. See that if you put it theta equal to 0, what kind of point it will become? If you put it theta equal to 0, what kind of point it will become? Please tell me. What kind of point it will become if you put theta equal to 0? If you put it theta equal to 0, the point will become what? An axial point. How much is the value coming? Mu naught by 4 pi m by r cube 1 plus 3. 1 plus 3 means what? 4 square root, and 4 square root means what? 2 will come. That means mu naught by 4 pi to m by r cube will be our answer. If you put it theta equal to 90, what kind of point it will become? Equatorial point it will become. The value will come how much? Mu naught by 4 pi m by r cube. So this is what you can also keep in mind. This is magnetic field, magnetic field due to short dipole, due to what? Due to a short dipole at which point? At a general point, you can say that, which is neither equatorial nor axial, but which formula will be applicable for axial and equatorial as well. Can you find out what is this angle alpha? Please tell me, if I want to calculate this angle alpha, can I say that this angle alpha will be this red component and this green component? So if you calculate the tan alpha, how much it will come? So tan alpha will come. Red component, how much is the red? This component? That component is mu naught by 4 pi m sine theta by r cube. Other component is mu naught by 4 pi 2m cos theta by r cube. So everything got cancelled out. What is the tan alpha coming to us? Tan alpha is coming tan theta whole divided by 2. So you can also find out the resultant is making how much angle with the direction of dipole. Sorry, not with the direction of dipole, direction of the line. With the dipole, if they ask you the angle, then you should answer theta plus alpha. Understood? With the line, if they're asking you the angle, you should answer it alpha. So please tell me, clear about the clear about this magnetic field calculation. Now, the different type of magnet. How do we decide these materials are what kind of? Okay. So depending on what is the value of the mu of a medium. Okay. Depending on the value of permeability of a medium, we can decide about a medium is or a material is diamagnetic, paramagnetic, or ferromagnetic. So actually there are three type of magnetic materials. Okay. And how do we decide about what kind of magnetic material we have? So type of magnetic material. So we have three type of, okay, what are these three type of magnetic material? So diamagnetic, paramagnetic, and ferromagnetic. Okay, di diamagnetic, diamagnetic. Next one is the paramagnetic, and the other one is the ferromagnetic. Okay, so diamagnetic, paramagnetic, and ferromagnetic. How do we decide about it? Depending on the permeability of the medium. Okay, depending on what? Depending on Just give me a moment. Okay. Permeability of medium. Just give me a moment. Okay. So depending on what kind of medium permeability we have three type of medium. Okay. What are the different type of medium? You can say diamagnetic, paramagnetic, and the ferromagnetic. Okay. So diamagnetic permeability is what? The diamagnetic permeability. The permeability means permeability of the medium we are discussing, isn't it? So diamagnetic material, if we have, then permeability of the medium will be less than mu naught. Okay. If a medium permeability is less than the vacuum permeability, okay. If the medium permeability is less than the vacuum permeability, that material must be a diamagnetic. Okay. Paramagnetic, what will happen? Paramagnetic permeability will be more than the vacuum permeability. Okay, clear? And ferromagnetic permeability will be what? Very, very greater than the vacuum permeability. So paramagnetic what? It is slightly greater than the vacuum permeability. But in ferromagnetic, it's a very high. Okay, so that's why what happened, if you keep a diamagnetic material in a external magnetic field, it will be repelled by the field. Okay, if a diamagnetic material is kept in a magnetic field, external magnetic field, okay, then what will happen? The diamagnetic material will be repelled in that magnetic field. Paramagnetic, it will be attracted but very weakly attracted. And ferromagnetic, it is going to be highly attracted. Understood? Clear? So all these material property, which material is a diamagnetic, paramagnetic, and ferromagnetic, it depends on what uh, what is the permeability of a given medium. Is that clear? Please tell me. Clear up to this?
Yes, sir.
Yes, sir.
Right. So now let's discuss the next part. So these are about what? These are about your permanent magnetic material. Understood? These are about what? The permanent magnetic material. Now we are going to discuss about that what will be the electromagnets. Electromagnets means what? If we allow current to flow in a current to flow through a conductor, then what is going to be the magnetic field produced by the current carrying conductor? Okay, so that kind of magnets are called as what? Electromagnet. Okay, so the electromagnet, what we are going to discuss in the electromagnet, we are going to discuss the, it is also called as the magnetic effect of current. Okay, electromagnets are also called as what? The magnetic effect of current. Okay, so let's discuss the next thing called electromagnet means what? Now we will discuss about the magnetic effect of current. Okay, so if current is flowing through a conductor, what will be the magnetic field produced by a current carrying conductor? Okay, so the first thing we have it in the magnetic effect of current is called the Biot-Savart law. So what is the Biot-Savart law? According to Biot-Savart law, any conductor is there. Okay, This conductor is having some current I flowing through it. Now we want to calculate the magnetic field due to this conductor. We want to calculate what? The magnetic field due to this conductor. So what we will do it? We will first calculate the magnetic field due to the small part of conductor, right? Because if you remember all these laws, whether the Coulomb's law of electrostatic, okay, you can say that, or Newton's law of gravitation, you can say that, isn't it? So all these laws are what? It is first given for what? The particles, small element, okay? And later, using the superposition theorem, we calculate for the bodies, isn't it? So here also Biot-Savart law, what it gives? It gives us the magnetic field due to a small current carrying element. So let's say this length of element is what? Something dl. What is this length? dl. And due to this small element, I want to calculate the magnetic field at this point. What is the distance? R. So this is the dl vector and this is what? The r vector. Understand the dl vector and r vector? dl is the small current carrying element. R is the position vector of the point where we want to calculate the magnetic field. So a small amount of magnetic field, if I am writing, and magnitude, let's write it first. Okay, now a small amount of magnetic field magnitude will come mu naught by 4 pi I dl sine theta by r square. Mu naught by 4 pi I dl sine theta by r square. What is the theta here? Theta is the angle between. What is the theta? Theta is the angle between dl vector and r vector. Okay. So magnetic field at any point due to a small current carrying element is how much? It is mu naught by 4 pi I dl sine theta. Okay. Mu naught by 4 pi I dl sine theta by r square we have. Okay. So if you want to write it in the vector form, what you can write it? dv vector will come mu naught by 4 pi I dl cross r. So when you will write it dl cross r, what it become? It will become dl r sine theta it will become. So isn't it denominator I should write it r cube I should write it? So check it, both are written the same thing. Only difference is what? The first expression of the magnetic field is only in the magnitude form and the second expression is what? It is in the vector form. So this law is called as what? It is called as the Biot-Savart law. Clear? Please tell me. This law is called as what? The Biot-Savart law. Understood? Please tell me. Clear? So Biot-Savart law, first it gave us for what? First it gave us for the uh, small element. What is the magnetic field will come? Now if we want to calculate due to a complete conductor, what is the magnetic field will come? Then what we have to do? We have to use the integration to calculate the net magnetic field. Okay. So let's try to calculate the magnetic field due to different type of conductor, straight conductor, how much magnetic field will come. Okay. Now, what is the direction of magnetic field? So direction of magnetic field will be what? Please tell me. Direction of magnetic field using the right hand thumb rule we can use it, right? It is dl cross r. So keep your fingers in the direction of dl and curl towards r. Then thumb will point towards the direction of magnetic field. There is another way to calculate the or to understand the direction of magnetic field. Okay, right? And what is that method? It's a simple like this. Let's say this is a conductor whose magnetic field we want to calculate. So hold the conductor. Okay, just hold the conductor here, and where you want to calculate, just spread your fingers in that direction. Then where your palm will be representing, that will be the direction of what? The magnetic field. Is that clear? Do you understand this method? Like, if you have current in the conductor like this and we want to calculate magnetic field here, just hold the conductor like this, and where you want to calculate the magnetic field, just keep your fingers there. So whatever the direction your palm is representing, that is the direction of what? The magnetic field lines at that point. Okay. So now let's calculate using the Biot-Savart law. What is the magnetic field due to a straight conductor? Let's calculate the magnetic field due to what? A straight conductor. And then special cases will be there. If it is a very long conductor, what is the magnetic field will come? Means infinite wire. Very long conductor means infinite wire also, we can say that, isn't it? If it is a semi-infinite wire, what is the magnetic field will come? So these things we are going to calculate it now. So magnetic field due to a straight conductor. Then we will also calculate it due to circular loop, how much it will come. Okay. So let's first calculate it, magnetic field due to what? The straight conductor. Okay. Let's say there is a straight conductor here. Okay. This conductor is having current I like this. We want to calculate the magnetic field at this point, and the perpendicular distance is given as something, let's say A. Okay. At what distance? Let's say this is a straight conductor having current in this direction. There is a point. What distance from the wire? A distance from the wire. This A is what? Perpendicular distance. We want to calculate the magnetic field at this point. So what we should do it? If I want to calculate magnetic field, first of all, I will consider a small element. Let me take at a distance x a small element, and what is the length of this small element? It is dx. Okay. So what I will do first? First, I will calculate the magnetic field due to this small element. And will I call this vector as the r vector? Do you understand the dx vector and r vector? Please check it. Earlier we have written dl vector. That same thing I am writing now as the dx vector. Okay, now dl and dx vector is the same thing. And r vector is what? R vector is the vector joining the current element and that point. Okay, R vector is what? It's a vector joining the current element and that point. Okay, let me call this angle as something theta. So can you tell me what is the magnetic field due to a small element will come? First of all, tell me dB. So will it come? Just tell me the magnitude. Will it come mu naught by 4 pi I dx sine? Can you tell me what I should write it here? I dx sine. What next? As per Biot-Savart law, what is the magnetic field due to an element? Mu naught by 4 pi I dl sine theta by r square. Right? But if you look at the expression carefully, the theta is what? The theta is the angle between dx vector and r vector. Is the theta in my question in this diagram in front of you? Is the theta is the angle between dx and r? No. What is the angle between dx and r? Angle between dx and r is this one. So this is 90. This is theta. This is 90 minus theta. So actually this angle is 90 plus theta. So here I should write it sine of 90 plus theta divided by r square. And if you calculate the direction, is it coming into the plane? Check it. Check the direction. If you keep your thumb in the direction of current and fingers where you want to calculate, Is your palm is representing into the plane? So a general representation is into the plane is represented as what? Into the plane is represented as cross. How it is into the plane represented? Cross. And how out of the plane representation happen? Out of the plane is represented as what? The dot. So you see that every element is creating the magnetic field which direction? Into the plane at that point. It means what? We need to add all those magnetic field, isn't it? If you have all the small element is creating the magnetic field in the same direction, then we should just add them, isn't it? To add them means what? We should integrate them. So the net magnetic field at this point will come how much? Integration of mu naught by 4 pi I dx, and sine 90 plus theta is the cos theta by r square. But if you look at, there are how many variables? Actually, we have three variables in this question. As the element changes, x will change. And if I take different element, theta will change. And also what will change? R will change. So there are three variables in this integration. So we can't do it. What we have to do, we have to bring it into single variable. How do I bring it? Let's see. Can I write it? Cos theta will come A by R. Please check it. Cos theta. Look at the diagram. Look at the diagram. Can we write it? Cos theta equal to A by R. So what is the R we have? R we have A. R we have what? R we have A cos theta. A by cos theta. A by cos theta means A sec theta. I'm going to convert everything into theta variable. Okay. So R is replaced in terms of theta. A is a constant in the problem. No need to worry. Next, how do we convert x into theta? So for that, can you say that? Sorry. Can you say that if you look at the same triangle, can you say tan theta value? Look at the tan theta value. So if you look at the tan theta value, is that x by a? So that means x is equal to a tan theta. And if you differentiate it, so dx will become a tan theta differentiation sec square theta into d theta. Now everything got converted into theta variable, right? So let's put the value and integrate it. Mu naught by 4 pi common constant I, no problem. dx I can write it as a sec square theta d theta. Cos theta leave as it is. R square. R square means a square sec square theta. See that after simplification, sec square theta got cancelled out. One of the a got cancelled out. Do I have mu naught by 4 pi I by a integration of cos theta d theta? And isn't it a very simple integration of cos theta d theta? Cos theta d theta integration will come just sine theta. We just need to keep the limit of this integration. The limit means what? Where the two ends are. So let's say this end is going at alpha and this end is completing at what angle? Beta. So what will be our limit of integration? Alpha and beta. But here also we need to be careful about how do we keep the alpha and beta. You can't keep both of them positive. Because why? Because one angle is measured in the anti-clockwise, other angle is measured in the clockwise. And as per the sign convention, anti-clockwise is positive, clockwise is negative. So we can put it plus alpha and we can put it here minus beta. So if you integrate it, what we are getting? Mu naught by 4 pi I by A, and cos theta d theta integration sine theta, right? Put the upper limit, sine alpha minus lower limit, sine minus beta. Sine minus beta is minus sine beta. So this is the magnetic field due to a straight conductor comes. How much is that? Mu naught by 4 pi I by A into sine alpha plus sine beta. Clear? Please tell me, clear this one? Now, what are the special cases we have? The special cases we have like infinite wire or very long wire. Okay. So some cases we have like infinite wire or infinite conductor. Infinite conductor, or sometimes they will use the word long straight conductor. A very long straight conductor is given to us. So what will be the magnetic field due to that one? If it is a very long straight conductor, that means what is going to be my alpha beta? This end is at infinity, this end is at infinity, and we want to calculate at a distance a from that. Magnetic field, what direction will come? Into the plane, because if you look at the direction of current and spread your fingers at that point, the magnetic field, palm is pointing into the plane. So what is the magnetic field coming? Mu naught by 4 pi I by A, and if it's a very long one, alpha beta will approximately how much it will come? 90 and 90. So how much the magnetic field will come? It will come mu naught 90 90 1 1. So mu naught I by 2 pi A will come. Understood? Acha, can you tell me? Let me take the second case and then you answer that thing also. If I take semi-infinite wire, second case, what I am taking? Semi-infinite. Semi-infinite means what? One end is at infinity and other end is here. And this is the point where we want to calculate. How much the magnetic field will come now? So magnetic field will come mu naught by 4 pi I by A alpha beta. So one end is infinity, so one angle will be 90. What about the other angle? Other angle can be 0 or can be having some other value also. But in this question, what will happen? If you look at the second end, is the second end, this point is at this perpendicular line itself. So the other angle will become 0 in this case. So what are we getting? Mu naught by 4 pi A, or mu naught I by 4 pi A we are getting. Clear? Okay. Any wire is given to us. Just tell me, if I ask you magnetic field due to a wire at a point, think about it. And I want to calculate the magnetic field due to wire at this point. Can you tell me what is the magnetic field at P will come? Is that going to come 0? And can you tell me the reason why the magnetic field at point P is 0? Because if you calculate magnetic field due to a current carrying wire at a point which is along the wire itself, maybe in the direction of current, maybe opposite of the direction of current. If the point is along the wire, then magnetic field will come 0. Why? Because the angle between DL and R will be either 0 or 180 degree. And if angle between DL vector and R vector is 0 or 180 degree, then how much the magnetic field will come? The magnetic field will come 0 will come. Understood? The magnetic field, when it will come 0? If a point is there, okay, if a point is there in such a way that if a point is there in such a way that the point is lying along the wire itself, then at that point the magnetic field will come how much? It will come 0. Clear? Clear? Please tell me.
Yes, sir.
Yes, sir.
So this is about the straight conductor. Next, we will discuss about the circular loop, how much the magnetic field will come, and then we will discuss about the combination also. Okay, please tell me. Clear? Right. So let's meet it tomorrow, and we'll discuss about the magnetic field due to the this circular loop also. Okay, right. So please tell me. Clear up to this? What we have discussed?
Yes, sir.
Right. Let's meet it tomorrow. Tomorrow morning. Okay, na? And then we'll continue with that one. Right.